One of the more straightforward ways of forming ionic compounds is using this method called the Criss-Cross method. It's fairly straightforward, fairly easy to do. It doesn't require a lot of math and manipulation, but you do have to understand how to do what oxidation numbers are and how to assign them. Okay, so here are the objectives of the lesson. How do we identify what compounds are ionic? How do we assign the proper ionic charges to each ion? And how do we determine the correct formula with using the Criss-Cross method? What you need to know already before you continue with the lesson: understanding of the periodic table and the location of the metallic and nonmetallic elements, definition of an ion and polyatomic ion, and the definitions of cation and anion. Ionic compounds are composed of cations and anions chemically combined. Remember, the metallic elements form the cations, the nonmetallic elements form the anions. There's a couple of exceptions. Ammonium ion is a cation, and hydrogen can either be a cation or an anion depending on the situation. When hydrogen is bonding to a metal atom, it's generally considered to be an anion. Ionic compounds are neutral in overall charge, even though they are made up of charged species. The net overall charge is 0. They're called salts, and some of their properties are they're hard, they're brittle, they conduct electricity when then dissolved in aqueous form or in molten form. Now, in order for the Criss-Cross method to work, we need to understand what oxidation numbers are of the ions. So the oxidation number is the charge of the element or polyatomic ion in the ionic compound. Remember, I said the ionic compound itself is neutral, but there are charges in the ionic compound. The oxidation number is based on the element's location on the periodic table. All elements in the same group have the same oxidation number, except for the transition elements, which can have multiple oxidation numbers. Right, but all the other groups, groups 1, 2, 13, 14, 15, 16, and 17, and 18, all of those elements in those groups, in their specific group, have the same oxidation number. And the oxidation number is based on the number of electrons that an element loses or gains to achieve a stable octet. The goal in bonding is to achieve a stable octet for both elements. So metallic elements are going to have a plus oxidation number, and the nonmetallic elements are going to have a negative oxidation number. So as mentioned, oxidation numbers are based on the location of that particular element in the periodic table. And the way I always look at it is the following. In order for an element to achieve a stable octet, is it easier for the element to lose electrons or gain electrons to get to that stable octet? That will have a relevance on the oxidation number of that particular element. So let's look at the periodic table and determine which elements are going to have negative oxidation numbers and which ones are going to have positive oxidation numbers. So our first group, group 1, all these elements here, their goal is to achieve a stable octet by either gaining or losing electrons. Let's look at group 1 here. Group 1, this column here, each one of those elements has a 1 valence electron. And so, is it easier to lose that 1 valence electron to look more like the inert gases here, or gain 7 electrons in order to make that look like these inert gases? Because we all want to look like this as far as electron stability, as far as the electron configuration, right? A full shell. So you should say, well, it's probably easier to lose 1, and that would be the case. So if you lose 1 electron, what is the net charge of your ion now? It's going to be plus 1. So all of these elements here, group 1, the alkali metals, are going to be plus 1. So let's write that down up here. So it's going to be plus and then 1. Now what about the other elements here? So what about group 2, which has 2 valence electrons? So group 2, this is this group here. Is it easier to lose the 2 electrons to look more like this, or gain 6 to look more like this? And you would probably say, well, it's probably easier to lose 2. So when we lose 2 electrons, we become +2. So we'll put that there, right? Now we're going to skip over all the transition elements because they can have multiple oxidation numbers. But let's go to group 13. So group 13, remember these have 3 valence electrons. So is it easier to lose the 3 or gain 5? And you would probably say, well, it's probably easier to lose 3. So we're going to put, and once you lose 3, you become more plus charge, so that's +3. Now here's the flip point. In this column here, these have 4 valence electrons. So if our goal is to get to valence electrons at 8 or 0, in other words, so a full shell, is it easier to gain 4 or lose 4? And you would say, well, it's probably the same. So we're going to have, this one is going to be the inflection point, and we're going to say it's going to be +4 or -4. Okay? Now we go back to the nitrogen column, so group 15. That has 5 valence electrons already, so is it going to be easier to get rid of those 5 or gain 3? You're going to say it's probably easier to gain 3, so if we gain 3, we get -3. And then you could go down the line here and say this is going to be -2. This is going to be, the halogens are always -1. And our last column is 0. Why is it 0? Because it doesn't want to gain or lose electrons. It already has a stable shell. That's why they're inert. They don't want to bond with anybody. So these are the oxidation numbers, and each column here has the same oxidation number assigned that's right above it. Alright, so let's form an ionic compound using the Criss-Cross method and the oxidation numbers we just assigned. So step 1, assign the appropriate oxidation numbers to the cation and the anion and place them as a superscript for the element or polyatomic ion. So we're going to use our periodic table, find the element that's making up, find the elements that are making up the ionic compound, assign the appropriate oxidation numbers, and put them as superscripts above each element. Drop the plus and minus from the appropriate element for the oxidation number, crisscross the numbers, making the superscript for the cation, the subscript for the anion, and vice versa. And then when you're done, you're going to reduce the subscripts to the whole number ratios. This is very important. You've got to do this. Remember to look at this, okay? What I mean by whole number ratios is if you try to reduce it any further, you can't. Alright, so let's walk through the steps and see how we can do it for a compound made from aluminum and oxygen. So first we're going to find aluminum and oxygen in our periodic table and assign the proper oxidation numbers. So if you look on your column, you can see that aluminum is 3+, and oxygen is 2-. So there's my 2-. Now you also may see it written like this, which is perfectly acceptable too, +3 and -2. I usually write it the other way. It doesn't matter. They're both the same. So don't be confused if you see it one way or the other. They're both the same. Alright, so you're going to drop the pluses and minuses and from the appropriate element. So we've done that here. And then we just crisscross them. So now that the superscript for the aluminum becomes the subscript for the oxygen and vice versa. And when we do that, we get Al2O3, as you can see here. And now we reduce to the lowest whole number ratio, and that is the lowest whole number ratio, so that we would stop there. Now let's say you got one where the numbers were something like this, Ca2O2. Is that the lowest whole number ratio? It is not, because you could divide each side by 2 to get CaO. So that's what I mean by lowest whole number ratio. So let's look at some examples from various elements to make some ionic compounds. So you're going to need your periodic table to do this. So the first thing we're going to do is we're going to look at the cation and the anion. And the first one is sodium and chlorine. So I look at my periodic table and I say that sodium is this. And I know that it's a 1+ charge. And then I know the chlorine is going to be 1- charge. Then all I'm going to do now is do my crisscross. So now my 1 becomes here, and my 1 becomes here. And so my final formula would be NaCl. Now we don't write the ones, right? I've told you that before. We don't write ones. It's just assumed. All right, the next one is magnesium and oxygen. So magnesium, we know that's 2 plus. And we know that oxygen is 2 minus. So we're going to do the crisscross again. So we drop the pluses and minuses. We cross them. And then we get Mg2O2. Now remember, we gotta leave that, we're not final form, because we can divide each one of the subscripts by 2 to get MgO, and that would be your final form. This is not reduced to the final lowest whole number ratio. So we can do the same thing for barium. All right, so barium is 2 plus, and then fluorine is, all the halogens are always 1 minus. So then we do the crisscross, right? And so we get final one with this would be barium fluoride. All right, and then the next one is the ammonium ion. Now remember, the ammonium ion is NH4 plus. That's on your polyatomic ion sheet. So the whole thing is NH4 plus 1. It's not just the H, so that's plus 1. That's a 1. And now the phosphorus is going to be 3 minus. So now here's where we get the parentheses have to come into play. So when we do our crisscross, we can see that there is more than one NH4 now, because it's going to have 3. So what we're going to do is we need to put parentheses around the NH4, because remember, the NH4 is plus 1, not the H or the N, and then phosphorus. And the last thing too with aluminum hydroxide, very similar. We have aluminum 3 plus. Find the hydroxide on your polyatomic sheet, and that's minus 1. Again, it's minus 1 for the whole thing, not just the H. So we do our crisscross again. So that comes here, that comes here, and then we get, again, we need to have the brackets because we have more than one OH. So we have AlOH3. And that pretty much sums it up. So again, assign the proper oxidation numbers as superscripts, crisscross them without the pluses and minuses, and then reduce to the lowest whole number ratio when you're finished. Okay, at this point in the video, this is where I make you stop the video and work the problems to do a self-check. Now you're going to need your periodic table with your assigned oxidation numbers, and you're also going to need your polyatomic ion sheet that has the oxidation numbers or the charges on those on the sheet. So check the back of your periodic table. It should be there, or look at the other sheet that I gave you for the polyatomic ions. Once you get that, you should be able to do this whole thing without any problem. So when you're ready, stop the video, work the problems, and restart the video when you want the answers. So stop the video now. Okay, so here are the answers, and hopefully you got them all right. Couple of things to point out. Some people may have gotten Ba2O2. Remember, we have to reduce the subscripts to the smallest whole number ratio. So you could have reduced each of those by 2 to get BaO. The other thing you have to be cognizant of is the placement of the parentheses. Remember, it's the whole unit that has the charge, not just part of it. So if you don't put the parentheses on it, it's just going to refer to the nearest atom. If you still struggle with this, you should come find me, or go back and review your notes to see if you can figure it out.